Hi there, I'm Dr. Ben Britton. This is the final section of the Introduction to Electron Backscatter Diffraction lecture. So in this I'm going to show you, hopefully it's a bit more light than the rest, but this gives some future directions and possibilities and potential for EBSD type analysis. So the future directions, we're going to look briefly at three-dimensional EBSD, so how you can combine serial sectioning in EBSD. We're going to look at a different geometry called transmission Kukuchi diffraction that is effectively doing EBSD on a TEM foil that gives you higher spatial resolution. I'm going to show you a little bit of high angular resolution EBSD, which enables you to look at the evidence of plastic strain and to measure the variations in elastic strain. I'm going to talk a little bit to pattern matching methods. I'm going to talk a little bit about some data fusion approaches where we combine EDS data more formally with EBSD. And one example of an in situ experiment where you can have some external actuation and measure the EBSD maps sequentially. So 3D EBSD, effectively this method, you reveal a new section of your sample and you conduct an EBSD map. You then effectively can construct a three-dimensional volume if you can reconstruct the alignments. The 3D volume can be done through mechanical polishing. You can do broad iron beams, so you can effectively use something like the PEX to sequentially cut through your sample and remove bits of this. There are methods to use a femtosecond laser to serially ablate the surface, and you can do fib-based EBSD, either with a gallium fib or a plasma sort of xenon fib to remove volumes. Once you've reconstructed the microstructure, you now have well-labeled data because you have effectively orientations for every point. It means you can get effectively well-oriented specific grains, etc. You have to be careful about the reconstruction of what the three-dimensional facets look like, but then you can look effectively, for instance, at the surface planes in 3 dimensions, the grain shapes, etc. An important aspect here is that this is very expensive to do, and so an important question is what is new that you want to learn that you cannot get from clever 2D measurements. So clever 2D measurements, stereology and statistics can get you a lot of information that 3D will get you. And similarly, 2D map plus, for instance, cutting a trench can give you access to a whole range of useful information about, for instance, the grain boundary subsurface planes, as we've seen briefly before. Transmission Kukuchi diffraction, this is effectively collecting from thin TEM-like foils, so we have a specialist holder to pull the SEM stage out of the way. We can then put the electron beam through the sample. The sample will diffract from the bottom face, the bottom, say, 20 nanometers, and we will produce a diffraction pattern that we can interrogate. The major aspect here is that we have a very wide angle diffraction pattern, and we can use conventional EBSD algorithms for that. We can also do things like use EDS to do simultaneous analysis, but do note that the scattering cross-section for the EDS is much lower, so the signal-to-noise for EDS may be poorer. This can be very useful though. We'll notice the scale bar. You can do, I've seen transmission Kukuchi diffraction with, say, a 2 nanometer step size. But there are huge issues of sample preparation and drift issues. So this is not a trivial experiment, but it is possible, and perhaps sometimes it's easier than doing orientation mapping in the TEM. There is a fantastic review by Glenn Snedden et al. That talks you through TKD and references some of the more primary literature as well on that. An area of expertise that I've been working on for many years together with Angus Wilkinson is assessing high-resolution EBSD to measure elastic strain. Very simply, if you have your diffraction pattern, if you strain the crystal, you change the interplanar angles, and by therefore tracking the zone axis shifts in the diffraction pattern, we can track and work out the interplanar angle variations and work out the deviatoric elastic strain variations. This is described in the Materials Today paper, but it's a nice example. So we measure the strain with respect to a reference point. It's not absolute strain. In this example, it's far field from the deformation. And we can, in this example, you can imagine effectively if you have your indenter, you push it into your sample, you have the material is effectively going to compress along the x-axis, and so you have a compressive stress field or strain field along the x-axis. You have a compressive strain field along the y-axis in this sense. You have a tensile 1-1, so horizontal strain along this axis, which forms cracks in the material. It's lesser in magnitude because it's cracked and released that tensile stress. The shear is a bit more hard to work out, but it is true, this variation. And you can also get the out of plane strain with a bit of cleverness, and that shows you effectively that the material is effectively under tension at the surface, which is important for lots of reasons in this problem. You can also measure the lattice rotation, so the variation in orientation with respect to the reference point, with exquisitely high precision. That's that 2 orders of magnitude better. This, again, just if you imagine the example that I talked about, if you push into the material will rotate positive and negative either side of that indenter crater, as shown. And so that effectively is that positive and negative lobe either side. So that's the rotation about the y-axis. This is the rotation about the x-axis in this example. And then this is the in-plane rotation, which is a bit more tricky to get, but that's related to the cracking process in the system. The lattice rotations are very useful if you want to understand the storage of dislocations. And so one simple example is to consider the edge dislocation array that's shown here. That if you imagine basically putting a series of extra wedges due to the excess dislocations, that gives rise to a bending of crystal A with respect to crystal B. If you measure orientation A, measure orientation B, and you know the spacing, you can work out the density of dislocations. So if you put more dislocations in this boundary, it will bend more, and if you put less, it will bend less. So you calculate the curvatures, use a process called Nye's dislocation density tensor to relate the curvature to the dislocation content. As a formal sense, the G&D analysis, the excess or geometrically necessary dislocations, is related to the kernel average misorientation, but G&D is more physical, specifically as it involves a step size. It's a curvature, it's a rate of change of gradient orientation with respect to distance. It's very useful, we use it lots. This is just an example that Jim Hickey and I did, effectively where he did a Vickers indent in a polycrystal steel sample, one of the ones you saw earlier, and we see effectively that there is a storage of accumulated dislocations around the indenter impression. We get grain-to-grain variation in the accumulated dislocation density. We get accumulating against some but not all grain boundaries. And we are quantitative in the log of the stored dislocation density. So that's the number of dislocations per unit volume. And that's very useful. We use it in lots of examples. This is related to the cam. So if you imagine the cam is describing the orientation variation of the center pixel with respect to its neighborhood. In our wedge example, if we had that wedge, so in the wedge example, we effectively have our crystal, or one example is like this. If you then had your pixels measuring like this, you will see that effectively there is a misorientation angle, so delta theta over here, and delta theta on this side. And so the region where there effectively is that high array, just let me check. I think the dislocations, I'm probably going to get the sign wrong, but I'm going to suggest they're this way around. I may be wrong. Please do correct me if I'm wrong, but yeah, I think it's that way around. Effectively, that will give rise to these pixels having a high misorientation with respect to their neighbors, so the cam value for that low angle grain boundary would be high. And that's the basic idea for cam. Importantly, and if you're going to use cam analysis, it's resolution dependent based upon how good your Hoff-based approach is doing. There are some systematic issues. It ignores the axis of rotation, and specifically the cam does not include step size. So you need to have a consistent step size between measurements for your cam to be valuable to tell you a story about your problem. The exclamation mark, this is a signature of plastic strain. It's effectively the stored the cam value is related to the stored excess dislocation content. This is not the plastic strain in your material. Plastic strain, first and foremost, is a tensor. The cam is a scalar value. Another advancing method, it's sort of in between high-res EBSD and conventional, is that we can do pattern matching. This was introduced in many ways, in one instance with regards to what's called the dictionary indexing approach by Mark de Graaf's group and colleagues in Chen et al. And so this is the OIM type indexing. This is the inner product from the dictionary indexing approach that shows effectively improved indexing specifically towards grain boundaries and also defects inside grains. So what you basically do is you sample multiple diffraction patterns from a reference dynamical calculation, and you try and find the best matching orientation with a well-spaced orientation spread. And so this shows the matching as plotted on this pole figure for the particular orientation of the input diffraction pattern and the output. We've also done this, and there's some in Astro EBSD of the method, where we have template matching against the dynamical calculations from dynamics. We do effectively a match against the template library, and then we introduce a refinement approach to effectively optimize the orientation solution within about 0.05 degrees in there, and that's described in more detail in Foden et al. If you produce the diffraction pattern, the simulated pattern from more than one phase, you can effectively do a phase classification problem, and so you can choose the best matching, best orientation, and so that can be useful as well, especially for poorer quality patterns. We can do data fusion approaches. So this is some work from Thibaut Dessolier, who's a postdoc in the Department of Materials at Imperial. He's been working on classifying multiple different carbides and silicides and other bits and pieces in some industrial alloys. And in this example, effectively by combining EDS analysis, so energy dispersive X-ray spectroscopy, plus EBSD patterns, we can effectively combine and segment our map to give us high quality input data that then we can effectively classify the chemistry from the EDS, and we can pattern match for the best quality phase. And so this effectively improves the segmentation, signal to noise, and a few other bits and pieces. A description of this is shown in the archive paper, and there's an initial description of this in Tom McClue's paper that's referenced on that Tom McClue's paper. The final example I think I've got for you is the in situ. So an in situ experiment, there are multiple, both heating, deformation, and a few others. But effectively in an in situ deformation experiment, you effectively do repeat mapping subject to external actuation. And in this case, they've effectively done a tensile deformation, and they've effectively unloaded to reduce creep, measured, reloaded, unloaded to reduce creep, measured, reloaded. And at each point for different amounts effectively of total strain in the location, they can see in this example the material is starting to do deformation twinning, and you can see also the increase in misorientation spreads and kernel average misorientation, specifically noticing it happens towards the interfaces of different microstructural features in this example. So with that, I very much hope you've made it to the end. I hope you've enjoyed. I'm very happy to take questions. There's a Q&A session, or feel free to drop me an email. That's b.britton, B-R-I-T-T-O-N, at imperial, imperil.ac.uk. Many of you will be aware that I'm leaving Imperial College London very